Okay, so today we are going to be talking about how you solve differential equations using the technique of separation of variables, and then we will look at some specific situations which are modeled by separable differential equations and how you can answer those kinds of problems. So what is meant, first off, by a differential equation? Well, a differential equation is just an equation that contains both a function and the derivatives of that function. So if our function is, y is a function of x, the differential equation will contain both y and y prime, or y double prime, or something like that. And in order to solve a differential equation, what you're trying to do is find an expression for that original function, y is a function of x. Now, not all differential equations are easily solvable. That's a bit of an understatement, but there is a class of differential equations that you can usually get an explicit solution, y is a function of x, for, and these are what are called separable differential equations. And we call them separable and differential equations because we can write them in this form. Okay, so the general form here is dy dx, so there's the derivative of the function that we're trying to find, the derivative of y with respect to x. And we can take the rest of the stuff that is in our differential equation and we can split it or separate it into sort of a function that involves x and a function that involves y. Now, i.e., what I've just written right here, separated into a function of x and a function of y. Okay? So if we've got something that looks like this and we want to solve it, what we can do is we can assume that one of our functions here, our function of y, is not equal to 0. We can define a new function, which is 1 over this original function. Then our differential equation here is the g at x part, so the part involving all of the x terms, divided by something involving all of the y terms. And if we can write it like this, we can cross-multiply and get a function of y times dy equals a function of x times dx. So basically, we can get all the stuff involving y on one side of the equation, all the stuff involving x on the other side of the equation, with a differential with respect to y and a differential with respect to x on one side. Okay? So if we get all of the y's on one side, y terms on one side, all the x terms on the other side, then we can take both of these sides and we can integrate them. Okay. So on one side, we're going to be integrating with respect to y. On the other side, we're going to be integrating with respect. So that kind of gets rid of the derivatives that we have here, and then the resulting thing can be solved for an expression in terms of y, something that is y equals whatever. And it's that y equals, that explicit expression for the function y, is what we're trying to find all along, and that is going to be the solution to our differential equation. Okay, so let's take a look at how this looks in practice here. Okay? We want to solve the differential equation dy dx equals x squared over y squared. Okay, so what makes this a differential equation? We have got an equation here involving x, involving y, and the derivative of y with respect to x. Okay? So first we'll find the general solution to this differential equation, and then we'll go ahead and we'll find the specific solution, just like we did back when we were working with antiderivatives. So this one's pretty nice here. We already can see how this separates apart. We've got all the x stuff up in the numerator on the right-hand side, all the y stuff down in the denominator. So we can just cross multiply and get y squared dy equals x squared dx. And then we're going to integrate both sides. So this is indefinite integration here. So if we integrate on the left, we're integrating with respect to y. So we don't have to consider, like in the past when we've been working with y, we had to consider it as a composite function. It was like y is a function of x. But because we're integrating with respect to y, we just treat y as our variable here. Okay? So y is not a composite function in this case. So if we integrate this, we get 1/3 y cubed plus a constant of integration, right? And I'm going to label it C1. Okay? And on the right-hand side, we're going to get the same thing, 1/3 x cubed plus a different constant of integration, C2. Now, immediately, we can take these two constants of integration and we can combine them together. I can subtract C1 from this side, and on the right-hand side, I'll get C2 minus C1. But that's just going to be another constant, which we still don't know what it is, so we're just going to call it C3. Okay? Where C3 is equal to C2 minus C1. Okay. Now we just want to take this thing that we have here and we want to solve for y. So if I multiply everything through by 3, I'm going to get y cubed is equal to x cubed plus 3c3. Okay. Now, C3 is just some constant. I don't know what it is. I'm multiplying it by 3. I'm just getting another constant. Okay, so it's still just a number. So if I wanted to, I could change that into a different constant like C4. But let's just go ahead and solve this thing for y here. We're going to have the cube root of x cubed plus, and I'll just call it, I'll just change it to C4. C4 equals 3C3. Okay? And that would be my solution. That would be the general solution to that separable differential equation. Now, if we want the solution that satisfies y at 0 is equal to 2, well, we just sub in 0 here to get the cube root of 0 cubed plus C4 must equal 2. So take, let's cube both sides to get 8 equals C4. So our specific solution here would be y equals the cube root of x cubed plus 8. Is our final solution. Okay. So we're just separable differential equations. We're just breaking it up into a bunch of x stuff, a bunch of y stuff, and then solving the two sides separately. So take a look at another example here. Okay, y primed is equal to x squared times y. So again, differential equation because it involves x, it involves y, and it involves the derivative of y here. So we'll think of this as y primed is dy dx is x squared times y. All right. So what we want to do here is get all of the stuff involving y onto the left side of the equation, all the stuff involving x onto the right side of the equation. So if I just divide both sides by y, dy divided by y, and at the same time multiply both sides by dx, I get x squared dx. So I've separated all the y terms to one side and separated all the x terms to the other side. And then we just want to integrate both of these sides. So I'll have the integral here of 1 over y dy is equal to the integral of x squared dx. Okay. So the integral on the right-hand side is exactly the same as in the last example. This is going to be 1/3 x cubed plus some constant here. Okay. And then on the left-hand side, the integral of 1 over y is going to be ln y. Okay. Now, something I've been kind of lax on up until now, but I should have been a little bit more specific about, is what we really mean here is the absolute value of y. Okay? Because if y is less than 0, ln y doesn't exist. Okay? So if y is less than 0, it doesn't make a difference if we've got 1 over y, but it does make a difference for the ln function. So we kind of solve this by taking the absolute value of it to make sure that the argument of that ln function is always positive. Okay? And we can deal with that, with the consequences of this absolute value, a little bit later when we're solving this equation. But from here, we want to get, and I should have a constant of integration on this side, but I know that I can always take that constant, combine it with the constant on the right-hand side, and so I've done that already. So I just have one constant of integration, okay, between these two. All right, now I want to take this and I want to solve it for y. Well, let's see. I can imagine changing this logarithmic function into an exponential function. So we'll get y is equal to, and I've got to take this whole right-hand side of the equation and put it as the exponent to base e. So that's e to the 1/3 x cubed plus c. Now, the exponent on the right-hand side is a little bit complicated, so we can break this up a little bit by, we've got an exponent where we're adding two things together with that one base. We can change that so instead of adding things up in the exponent, we're actually multiplying two powers together. So this is actually, we can think of this as e to the 1/3 x cubed times e to the c. Okay. Now, e to the c is just a number. It's e to some constant. So we can rewrite that as some other constant at some point. This is still absolute value of y. Okay. So if we want to take off the absolute value signs, we can get y equals plus or minus e to the c times e to the 1/3 x cubed. Okay. And I'm going to just take all of this, okay, plus minus the e to the c, and I'm going to turn it into some new constant that I'm going to call, I'll only use c from now on. Okay, I'll call it c1. Okay. Okay. So that would be our general solution. Y equals some constant c1 e to the 1/3 x to the power of 3, And this constant C1 can be, well, you would have to have a specific solution in order to figure out what it is. It can be positive, it can be negative, but it's just some constant. All right. Okay. I'm not entirely sure why I've included this example. It is a differential equation because it involves functions of, the equation involves y in two different places. It involves x and it involves the derivative of x. It's a separable differential equation, okay, because we can see all of the y stuff is on the denominator, all the x stuff is already up in the numerator. So we could easily separate this into 2y plus cos y dy, 6x squared dx. And then we can integrate both sides. Okay. On the right-hand side, we're going to have 2x cubed. I'll put my constant of integration over there on the right. And then on the left-hand side, we're going to have y squared sine y, y squared plus sine y. Okay. Now, what we would want to do from here is rearrange this to get an expression for our function. So solve for y here. This one cannot be solved explicitly. Like, we can't get this to the form y equals some function here because of the squared and because of the sine. So this is, I mean, what we say here is this cannot be solved explicitly. But if we were given some information about, some more information about y and about x, it's possible that we could sub that information into this function and get something out of it. Okay? But we can't get it into explicit functions. So that is separable differential equations.